Okay, so thank you for coming at the end of a long day of lectures. And I know you must be tired, but I think I was here for a very few days, so Alikram had to squeeze in the schedule, so I apologize for that. The best way to stay awake at this late hour is to keep asking me questions. So like we did last time, just stop me whenever you have a question, and then we should have fun with this. We have last time looked at what the black hole puzzle was, and we saw it was a really serious puzzle because you cannot delicately encode the information in some way in the Hawking radiation. So the only way to solve it is to make some radical change. Well, that's basically why the puzzle wasn't solved for like a good 40 years since the time it was proposed. And we have said that we'll end up with, at the end of our discussion, the goal was to understand that there'll actually be a radical change to how we think about quantum gravity. Normally, if you just do dimensional analysis, you think quantum gravity should become relevant once you go to wavelengths below the Planck length. But in fact, that's not the case. That's the case if you collide just a couple of particles. But if a large number, n of particles are involved in the process, so like when you make a black hole, you need a large number of quanta which are involved, the scale of quantum gravity, as found in string theory, jumps to a power of n times the Planck length, and then it becomes macroscopic. In fact, it will go all the way up to the black hole horizon, and in the end, I'll come back and give you some conjectures as to why this could also be very relevant in understanding what's happening in cosmology, in particular with the cosmological constant. So the issues we are addressing are really very important here, obviously. I'll be talking about a little bit of string theory today, and I know that many of you would not have seen string theory, but we don't actually need much out of it. All we need to see is just get a picture by looking at the simplest examples to see how this kind of magic is happening. Okay, so this is what we need to understand, and then the details, of course, if you want, you can go and read the string theory stuff. Okay, so let's begin with the idea of black hole entropy. So I know not all of you are familiar with this, but it's rather simple from where we were last time. We have seen that black holes emit Hawking radiation. They produce pairs. One guy goes in and one guy goes out as Hawking radiation. And we've also seen the natural scale in black hole dynamics. There's only one length scale, the horizon radius 2 gm, and that becomes the wavelength of the particles. So lambda is order gm. And then the temperature, of course, is 1 over the wavelength. You can see I've put h bar to 1 and c to 1. So the temperature is 1 by gm. When you actually do the calculation properly, you find that temperature is 1 over 8 pi gm. Okay, so that's the temperature at which the black hole is actually emitting these particles, which we had seen the last time. Okay, so now can we compute the entropy? Well, if you have a temperature, you can try to use this thermodynamic relation, TdS equals dE. Of course, because C is 1, E is just m. E was mc squared. So dE is just a change in the mass, dm. And so I have ds by dm is 8 pi gm, and that gives me S is equal to 4 pi gm squared. Okay, so without doing any much work, we have already concluded that if thermodynamics is to make sense, the black holes have an entropy. Does this number make any sense to us? Well, the area of the horizon is 4 pi times this radius square. Since the radius is 2 gm, the area of the horizon is given by this. And then if you look at what this S is, it has a factor of m squared, and so then you actually find, if you put the factors in, S is the area upon 4g. So this is the famous result. Initially, Bekenstein said that the entropy was proportional to the area. He didn't quite have an exact coefficient like the 4, but then after the work of Hawking radiation, you can just do this few lines calculation, and there you get a prediction for the entropy of the black hole. So if you want to see what this is in better terms, let's restore the C and H bar for a second, and then you see this is basically the area of the horizon measured units of Planck length squared. So if you take a solar mass black hole, it has a radius of 3 kilometers. You'd imagine that and break it into cells of radius Planck length each. Planck length is 10 to the power minus 33 centimeters. So lots of these little pieces, and if that's the entropy, there'll be e to the that number of states, and that's a huge number of states, and that's much more than the number of states you'd get for matter of the same energy. So somehow this is already telling you that black holes are liberating some new kind of quantum mechanical, quantum gravity degrees of freedom. Well, if a black hole has to have so many states, where are they? When people try to look at the black hole, you might have heard the phrase, black holes have no hair. They just seem to have one shape for a given mass, charge, and angular momentum. Well, if black holes only had one state, then the entropy would be log of the number of states, which is 0, and that's quite a bit different from this number. Okay? So there seems to be some puzzle. In every theory where black holes have no hair, there is an immediate contradiction. because you have the guy radiating, so you have a temperature. If you have a temperature, if thermodynamics is to be true, you have an entropy. You can even get precise value for it immediately. And once you have a value for the entropy, if StatMech is to make sense, there must be that many states. So of course, this is not a rigorous problem at this stage. You can all say that black holes have no hair, meaning the horizon always looks the same, but maybe there are differences near the singularity. Okay, so that would be okay to say, but nevertheless, still you can actually see the degrees of freedom and somehow count them to get the entropy. You haven't really understood what's going on with the black hole. Yes?
Sorry, this temperature is only related to the radiation, and
Yes.
it is, it is related to the horizon of the black hole. So
Yes.
there are absolutely no effects other than that can be accounted for the temperature. We are using the fact that anything that falls inside the given horizon goes to the singularity, so there should be no particles moving inside that region.
Yes, so as we had seen, the light cones inside are such that anything that falls in has to keep going in. So that whole region is the vacuum. If the whole black hole becomes the vacuum, then you're going to get Hawking's pair creation. And this is part of the puzzle, right? The computation of temperature was done just from looking near the horizon. In fact, that entire area is completely cleaned out. It's all the vacuum because everything has to keep falling in. So if this entropy really came from somewhere near the singularity, it would be a little unfair. It wouldn't make any physical sense. Why would you count the entropy near the singularity when the radiation is all coming out from the surface? So even if that could account for the entropy, it would be a little bit, not a good fit with things.
So that is not going to change in string theory as well?
So in string theory, we'll see what happens. Let's just see what happens in string theory. But in any theory of quantum gravity where you can't actually account for the entropy, you already have a problem. Okay, so before we get to the information paradox, you can see the first step must be to account for the entropy, and actually that is maybe the first major success of string theory, apart from the fact that it actually got us a theory with no loop divergences. It actually will get the entropy down completely correctly with the factor of 4. It's 1 over 4, A over 4G. So let's just go over roughly how string theory actually derives this number. So let's look at how you make black holes in string theory and compute the entropy. Once we have the entropy, we at least know what states we should be counting, and because that works out perfectly, we know we have a good theory of quantum gravity, and then what we are going to do is to actually take a look at what the states are. If you have a theory, you can count the states. With some effort, you can go and see what the states look like, and then we'll see whatever this magic we were looking for, that in fact the effects of quantum gravity will actually be over horizon scales. Okay, so here are the properties of string theory that are going to be relevant. The elementary objects, of course, every theory of quantum gravity has to have the graviton, but it also has these extended objects like strings, like the string loops, but they can also be extended sheets like 5 branes and some 3 branes. It doesn't really matter, but they're just stretchable sheets and things and so on, and other objects. And in fact, you can map any of these objects to other objects by dualities. We won't actually need any of that, but the important thing for us is the theory does have extended objects which can stretch. Okay, they're not all point-like particles. This is a point-like guy, but these are all extended guys. That's one curiosity of string theory. And then again, as we had noted in the public lecture as well, the coupling constant of the theory is actually a field, and so you can imagine it being small or large, and that's just a good technical tool, because normally if coupling is strong, you don't know how to do calculations, but you could first imagine it to be weak, do some calculation, then just imagine it to be increased, and you can sort of follow where it goes to strong coupling. So it gives you a lot of additional tools on how to think about things in string theory. And thirdly, the theory lives in 10 dimensions, and so some dimensions have to be compact circles in order to get our 3+1 world that we see. This is the part I like most about it. The theory is actually unique. So normally if you do some normal theory of particle physics, you have free choice of, what's my gauge group, what's my particle content, what are my couplings. But in fact, string theory gives you no freedom at all. The theory is completely fixed. In fact, which elementary objects you have, which strings, which branes, what are their tensions, their mass per unit lengths, their interactions are all completely fixed. So that's beautiful. If this thing works, it has to give us the black hole entropy correctly. And if we don't get the black hole entropy correctly, string theory is gone. Okay, so it's rather simple. There's nothing which we can tune to get the A by 4G. It either works or it doesn't work. Okay, so now how do we make a black hole? Since we can't add any new objects to the theory, we have to make a black hole using what we have. Okay, so here's a compact dimension, and so I just drawn one compact dimension but this is 3+1, these are 6 compact dimensions. You of course have gravitons, but if you try to put gravitons in some place, they basically just run away. It's not so easy to make a black hole with gravitons. So what you could do, the easiest way to make a black hole would be, you take a string and just wrap it around the compact direction. There's a loop, you wrap it around. Okay, so you stretch it there, and then the guy just is sitting in a point, it's not trying to go anywhere. And of course, that's not a very heavy object. If you want to make a big black hole, you'd like to take large amount of mass, so let's take many of these strings. To a person who can't actually see the size of the compact dimension because they're just about Planck length, it's a pretty small object, so then he will just see the non-compact dimension like the x, y, z that we see, and each of these guys just looks like a point mass. Okay. So that's the idea. We'll use the compact dimensions to wrap things on, and then if for somebody who can't resolve that, it just looks like a mass over here, and if you have a lot of mass, then, well, that's the only way to make what we would call a black hole. Of course, we don't actually want to get many different objects, because then we get lots of different objects, each of about Planck mass. That's not what we are looking for. We want to make one black hole of a large mass, which means we're going to take a bound state of these objects. So how do I make a bound state of many strings? Everything in string theory is actually very, very simple. The way you make a bound state of two strings is very simple. One string was a loop like this, other string was a loop like this. If you want to make a bound state, you take a string, after all, just like a rubber band, you wrap it like this, then once again, and then let it close. That's it. Everything is very simple and geometric. And that's the picture I have drawn here. The string goes around some number of times and just closes on itself. And then if you actually try to see what, if somebody can't resolve that small compact dimension, it'll just look like a big mass blob. It actually also carries a charge, and that's because these strings have a charge. A string wrapped this way is not the same as string wrapped that way. If this guy has a charge +1, the other guy has a charge -1. So of course this guy has a mass, but actually also has a charge, and the charge actually produces some kind of a gauge field, and in fact has mass equal to charge. So if we make a black hole out of this, it will be what's called an extremal black hole, okay, which has mass equal to charge. Well, it turns out that actually we haven't really managed to make a good black hole at this time. Either side. Well, if I wrap the string one way, it's plus. If I wrap it the other way, it's minus. If I wrap it partly this way and partly that way, I can do that, but then it's not really wrapped. It has no wrapping number, just a vibrating string. Those are non-extremal states, and they are more difficult to control. So it's easier to start with extremal states because you can easily see what they do, and that's very important because here it's very clear, right? If I wrap the string like this one way and leave it, the minimum energy state is the guy just sitting at one point, all tightly wrapped here and not doing anything. If I actually wrap some this way, some that way, it starts vibrating, then it can do more things.
What I'm trying to get at is that the proof goes through for the extremal state. Is that for convenience, or is it like a fundamental thing?
At this moment for convenience, but obviously we want to do the extremal one first and then move away to near extremal and try to go further. So it's a technical tool, but in the end you want all of them, absolutely. In the end you want all of them. But the whole game for string theory actually began with looking at extremal states, and so that's where we begin here. Okay, so this is again the picture. We have wrapped the string here. Somebody who can't resolve direction looks like a point mass. And so the thing to do is now to compute what kind of a metric does it create. If you put a point mass somewhere, you thought you might get a black hole around it, but actually you don't. The space looks like flat far away, like what I was showing you with my hands, and then there's like, the metric sort of comes in like this, like any picture in general relativity. But in fact, it all sort of ends at a point, and the area of the horizon is actually 0. Okay, so why is that? Well, I'll show you in the next slide why that happened, but anyway, if you work it all out, you find that the area is 0. Should we be happy or sad? Well, we didn't make a black hole, so you might be sad, but actually we should be happy. And the reason is that if we really wanted to prove this relation, that the entropy is A over 4G, if we had actually got something with a nice area, then this would be non-zero. And then we would have a problem, because the number of states you have, if you just wrap a rubber band on somewhere and just leave it, it's just one, because it just makes its minimal state. It's just sitting there, it's not doing anything. So it's just one state where the guy is wrapped and just sitting there. So you would get the entropy as just log of 1, where it's actually log of 256 because it's a supersymmetry multiplet and so on. But log of a finite number like that is basically 0. The important thing is it doesn't really grow with the mass. If I make this 1,000 or 1,000,000 or 10 million, the number of states doesn't grow, and that really wouldn't tally. If the area kept growing with the mass and this didn't grow, then the microscopic count of states will not actually match the area of entropy, and I would be in trouble. So we got like 0 equal to 0, but that's actually a nice thing. We didn't want to get something equal 0. So the entropy does not grow with the number n1, which is the number of times I have wrapped this around. Okay, I call it n1 because the one-dimensional object which I'm wrapping. If I'm wrapping a 5 brane, we call it n5 and so on. Yes?
Recently, Wafa proposed a Swapler conjecture. If I apply the Swapler conjecture to this calculation, would something change?
No, this doesn't have much to do with swarm plan.
Something reducing the number of vacuums.
No, so the things are actually going in different directions. So what happens is, depending on what different compactifications you use, Okay, you can get different low energy theories. As far as string theory is concerned, they're all valid low energy theories. And the black hole game has to work for every case, because for every compactification you can make a black hole, and the entropy and everything has to work for every case, right? What Wafa was talking about was the fact that if somebody comes and proposes a low energy theory just from randomly from somewhere and says this is a low energy limit of string theory, most often it might not be. But we are not doing that. We are actually taking the full string theory at all times.
I didn't mean, does that conflict with black hole issues? So,
So no, so right now there's no contradiction between the conjecture and this. They're sort of going in slightly different directions, because the swampland is talking about theories about which you don't really know where they came from. Right? Then you're asking, does it come from string theory? So here, if I try to take a black hole and I give it some random properties, not the properties from string theory, I will be in trouble actually. So you'll see actually as we do this, every property of string theory will have to be used exactly correctly down to the last factors of 2 to make the S equal to A over 4G. If I assume some random properties like happens when people do the swampland, like they just take some effective field theory, I will never get the entropy to work out. It will be some random number. So actually, yeah, in that way it's very relevant, but it's not a contradiction with the conjecture. It's a different game they are asking. Okay, so let's see why we got no entropy out of it. And that's because if you wrap a string on some circle like this is after all general relativity, right? The manifold can flex, it can bend. And if you wrap something, there's a lot of tension in there, and so the energy is minimized when that circle basically gets squeezed. Okay, and if you end up squeezing that circle, then in fact, actually you end up finding there's actually no area. So we didn't actually manage to make a good black hole yet, but that's because we squeezed this circle. So we need to actually do something so the circle doesn't squeeze. But if I wrap a string out there, it will tend to press that region, right? So how do I make it not press down? So what I can do is, so the reason it pressed down here was because the energy of a string is minimized if the length is minimized. Okay. Can I hope for something whose energy is maybe maximized when the length is minimized? Then maybe there'll be some balance. So who's the guy which if I put there, the energy will try to grow if I shrink the circle size? Let's look for something like that. And that's actually easy to find. You take a graviton which is running around a circle like this. How much energy does the graviton have? It's massless, so E is equal to P in units where C is 1. And if the length of the circle is L, then if the graviton carries NP units of momentum, the energy will be 2 pi over L, or 2 pi times some integer over L. Is this formula okay for everybody? This will be very basic for us. It's just the momentum of a particle on a circle. The wavelength will be L, and so the energy will be like 1 over L. Okay, so now what we should do is we should take not only the string, but also a graviton or some gravitons carrying some momentum, and then if we make a bound state of these together, now this is my picture of making a bound state, this guy will try to make the circle shrink, but the energy of this goes like 1 by L, it will try to make the circle expand, and the whole thing will come somewhere in the middle and stabilize. Maybe then I will get a black hole. Okay, so that's the game. That's how you always end up making black holes in string theory. You take different kinds of strings and branes or momentum modes or just the objects you have. When you make a bound state of them, then in fact you manage to make something where everything is stabilized and nothing pinches. Then you'll get a good horizon, and then you have a black hole. Okay. So let's see where we are going with this. So we just want to make now, we are trying to see where we need to go. We need to take this string and add some momentum to it, and let's see what we get. So do we have a physical picture of what's the bound state of momentum waves bound to a string? Now, as we said before, in every quantum mechanical problem, bound states are a complicated thing, but not in string theory. Everything is easy in string theory. So let's just make a picture. The string was wrapped like this. I can just imagine opening it up like this to its covering space. This total length is, if it was wrapped n1 times and the circle had length L, the total length LT, L total is n1 times L. I just open it up for my convenience. Is that okay? And then if I want to bind the graviton to it, that means I have to add momentum to a string. How do you add momentum to a string? You just add traveling waves on the string. Okay, we just take a string and you give it a shake, it carries momentum along it. That's the way you bind momentum to the string. Okay, I want to make a bound state, right? I don't separately want the gravitons floating here and the string floating here. Okay, so I just have to add a traveling wave to the string, and then I have a bound state which has both winding and momentum. Okay, good. This will actually give me a good black hole, at least better than before. Will I get any entropy here? Actually, you can already see where the entropy is coming from. Where's the entropy coming from? If I have a given amount of momentum on a string, which harmonic should the momentum be in? I can put it all in the lowest harmonic on the string. That's like one sine wave. Or I can put some in the lowest harmonic and some in the second harmonic. Some in the lowest harmonic, some in second, some in third. There are so many ways to partition it. They all have the same momentum charge. Any amount of momentum you carry in there looks like a definite charge from the dimensionally reduced point of view, and the winding looks like a charge from the dimensionally reduced point of view. But when I make a bound state, I've seen all I get a string with a certain length and a certain amount of momentum, and if I can partition the momentum in many ways on the string, well, those are all the states I can have. I can count them, and if that entropy comes out to be the A over 4G or whatever I want, I'm done. And that will be really beautiful. In fact, all the entropy of black holes, in fact, the celebrated result of Strominger and Waffa, it really is a small extension of what we already have here. This is all that you need to do. This is how entropy comes out in string theory. So let's just see how the calculation is done. It's very simple to do the calculation. So now it carries n1 units of winding charge, np units of momentum charge. We open it up to this covering space. If I have a quantum in the kth harmonic, it carries energy 2 pi k over L total. Is that clear? If I had the lowest harmonic on this, because the length is n1 times L total, its energy would be 2 pi over L total, right? If it in the second harmonic, each quantum carries 2 pi times 2 over L total. And so that's the amount of energy and momentum carried by one quantum of the kth harmonic. So the total momentum I have was 2 pi np over L. I can of course write it as 2 pi n1 np over L total, because L total was n1 L, just makes it look symmetric in the winding and momentum charges written in terms of L total. So this was by definition my momentum. So I have to put n1 np units of momentum on this opened up string, on the string of length L total, and I have this many units of momentum to partition in different ways. I just have to count the number of partitions of this integer. To make a big black hole, N1 will be big, lot of charges. NP will be big, okay, large amount of charges. If you have a large number here and you ask how many ways can you break it into pieces, that number is going to be large. You are counting what is mathematically called partitions. It's the number of ways to partition a number. So you have to partition n1, np among different harmonics. Suppose there are nk units of the harmonic k, then the total momentum is n1. If you have n1 units of the first harmonic, it gets that many units. If you have n2 units of the second harmonic, each one contributes twice as much, right? So 2n2 plus 3n3, or any way so that these numbers can be totaled up to n1, np. Any set of these numbers which will give this answer, counted as one possibility. So we have to find all the possible solutions to this equation. Well, how many solutions are there? It actually ends up growing exponentially. It's a very old mathematical problem. It goes back to the work of Ramanujan and Hardy from a long time ago. And the number of these partitions actually grows like square root of n1 np. Well then, if you want the entropy, it's the log of the number of states. Take the entropy, you can see it's growing like the number of charges. It's growing like the charge. That's roughly what you want, right? Because charge and mass basically sort of give you the radius of the thing. So when I go back and compute the area of the horizon, it will be something like this. And now you can see the entropy, the huge numbers we were looking for are already coming out for us. And they're just coming out, depending on how you actually want to put charges in strings and branes, they automatically spit out these numbers.
May I ask something?
Just one second. I think I don't know why there's a blank, but okay, I was here. Good, okay.
While calculating the momentum, shouldn't there be an uncertainty?
In the momentum. Okay, so not exactly. Because this momentum is in a compact direction, okay, it's actually a well-defined charge. Like if I have a circle, then the amount of momentum in that direction is a conserved quantity. On a circle, you can just have some n units of momentum.
But we represent it as a wave, right?
Yes.
So the wave itself induces an uncertainty.
Okay, so to an extent you're right. I mean, if you have a quantum running in a circle like this of length L, the reason it has to be a wave and has to spread out is because it has momentum. I mean, you can't put it in one position because then it will become very uncertain. So in fact, the fact that the wavelength has to be something, that's basically because of uncertainty principle. I have a compact length and there has to be some spread. But depending on how much the spread is, that spread itself is the wave function we're looking at. If I put it in the lowest harmonic, that's one way of spreading it out. If I put it in the next harmonic, that's a different way of spreading it out. But I do have to spread it out. And in fact, I'm actually computing all those spreads, the uncertainty principle spreads. When you start writing waves for anything, you are doing the uncertainty principle, right? I'm not in the classical limit where I had a point moving. If I took a point which was moving, I would have nothing to count. Absolutely, there would be nothing to count. I just get one state. But because it's a wave, it has a wavelength. That's how I got all these possibilities. So yes, this is very, very quantum already. Yes?
Where did you use the fact that it is a black hole in the proof?
So far, nothing. We are just trying to make all the possible states we can get by taking strings and branes with some charge. The black hole part will come now. Because all we have said is how do you make a black hole in any theory? You take the objects in the theory, a lot of them, bind them together, make a bound state, and stare at it. That's the only thing you can do. If it is a heavy object, it should make a black hole, or if it doesn't make a black hole, there's no black hole in the theory. That's all you can do. And so that's where we are starting. That's exactly what we're doing. So now, in fact, coming back exactly to your question, what we have done right now is that we have sort of made this stuff, and we have counted the states, and we get a count of some states. And now if we actually try to see what kind of metric does it produce. So far just talking of strings as if they were like free strings, right? But that's like what we call weak coupling. We're not letting them back react on the metric or anything. But as you said, if you let them back react on the metric, the thing tries to bend, it tries to squeeze, these guys try to make it not squeeze, the whole metric changes and bends. So well, you can do all that. And again, this time the metric looks like flat space at infinity. There is as like this. But this time actually, you can get a small area to open up here if you take into account the R squared terms in the Einstein action. It's a little delicate because we haven't done things which are very complicated yet. We've just taken string winding and momentum. So we have to use the Einstein equation, but also the R squared corrections. So because there's a small horizon which opens up. But if you take that small horizon which opens up, at least for some cases where people have done this carefully, if you actually compute the entropy, these are some corrections coming from R squared. So in this case, the answer actually becomes A by 2G and not A by 4G because of the R squared terms. But anyway, you get a very precise answer. And this precise answer you get by computing the area is exactly equal to the answer you got by computing all these partitions. Okay, so this in some sense was the origin of how you get black hole entropy. This idea actually goes back to initial comments by Susskind and then was worked out by Ashok Sen. The thing we are still not completely happy with at this stage is that this horizon is rather small, so the curvature squared couplings were as big as the curvature couplings, but the game actually keeps working the same way if you take more charges. What does more charges mean? You take one string which is winding, you take the momentum that we just put on it, and you can also stick in some 5 branes, some of these sheets. Okay, you can just keep putting more and more of those objects in string theory I showed you on the first slide. In each case, basically the same thing happens. You get some momentum waves and you have to partition them, and the entropy has the same form. If you had 2 kinds of charges like the winding and the momentum, the entropy goes like square root of n1, n2. If you had 3 kinds of charges, it goes like this. If you had 4 kinds of charges, you go like this. And if you start making things not extremal, like you put some winding and anti-winding, that's what you were asking about, you get actually square root of the winding and square root of the anti-winding. So that's the way the expressions work out. So the actual counting of how many states you have in string theory, when you take so many branes and so many anti-branes and so many of this kind of branes and so on, we know how to do that counting. I just showed you a simple case where we got this answer, but all the answers can be gotten in this fashion. So the microscopic count of states is very easy in string theory. And in fact, now when you make all those more complicated cases, in fact, this one was sort of borderline because the horizon was so small, the R squared terms were important in the Einstein action. But here the R squared terms are not important. These horizons can be made 3 kilometers large or as big as you want. And then you can actually use the formula A over 4G. You don't have to worry about R squared corrections, and the near extremal case was done by Karen Maldacena, the original result, a very important one by Strominger and Waffa, and you find an absolutely beautiful agreement. In every case, the microscopic entropy agrees with the area entropy. So this is actually a major success for string theory, because if the actual number of degrees of freedom which you're counting agrees with thermodynamic expectations for the entropy, it means you've got hold of all the right degrees of freedom. And here if you made a single mistake, like if you took the string tension and you made a mistake of a factor of 2 in it, this won't work out. You'll actually get, A by 4G, A by 2G, or A by 8G. You'll have a problem and it won't work out. So it really checks out the fact that you have all the tensions and the objects and everything are completely known to you. If the number of compact dimensions was changed from, let's say, 6 to 5, the entropy of the black hole in 4 dimensions will be off by a factor of 6 over 5. So it's really important that everything of string theory actually went in, including the fact that there were 6 compact dimensions for a 4-dimensional space down here. Yes?
You get the 1 by 4 as a sum of an infinite series.
It's not infinite actually. For any sum of any particular charges, the sum is actually finite, because you're partitioning all this to get a given number, right? Suppose this number is 1 million. There's still only a finite number of ways of partitioning it. Yeah, it's a finite sum. Okay, so that's the entropy story, but it hasn't actually solved the problem that we want to solve, because we're actually interested in the puzzle with Hawking radiation. But let's see if we get anywhere close to it. So here's a picture where we have string winding and the momentum and so on. I talked about all that. This green stuff is 5 branes. I said you can stick in the 5 branes also. I'm just drawing a picture, so let me stick it all in. And then these strings, you can make them have momentum and anti-momentum. You can have winding and anti-winding. You can put all those things to make it non-extremal. And then they radiate, and you can actually compute the rate of radiation. And if you do that, you find a rate of radiation from here. It's called the gamma of the microscopic calculation. Gamma is usually used for rate of radiation. It actually exactly matches the Hawking rate of radiation. This is the Hawking pair production process, just drawn in cartoon form. So that's remarkable also, because not only do we seem to understand these states and their counting, if you actually compute the radiation, even that completely matches out. Okay, so it seems that string theory seems to know what it's doing. It seems to understand black holes. But then what happened to our information paradox? So far we haven't solved that, because this is a completely unitary process. There's no information loss here. If you have a vibrating string and it emits something, all the information is there. If the string is vibrating this way, it will emit a sound wave like this with this polarization. If it was vibrating this way, it will emit a sound wave with this polarization. Okay, so there's no loss of information or anything. But when you look at a black hole, the radiation comes out of the vacuum. Remember, the whole thing was pulled out of the vacuum. So even though these two rates agree, there's still something completely missing. This is a process which doesn't have the same information issues as this process that Hawking found. This is a weak coupling calculation, but it still seems that if this is what was happening at strong coupling, if we got normal black hole with a normal horizon, and then we couldn't stop the pair production, we would still have a problem over here. So now let's go back and see what the solution to the information puzzle is. We haven't come close to that. We have just seen how to make black holes, and we have seen that if we make them, at least they make sense because the entropy is correct. So let's see if there are any questions at this stage. I'll just switch gears now to the structure of the black hole. Okay, so now we come to the fuzzball construction. What's the solution to the information paradox? Well, we already said that we are wrapping this string here, same picture as before. We wrap it in one time. We have NP units of momentum. You can open it up, and then it's just the bound state is basically all the different ways you can make a traveling wave. We call this the covering space, right? You open this up, so it's called the covering space. Okay, so now this is exactly the same as before. A string carrying the momentum carries it in the form of a traveling wave. Well, here comes the important thing. If you take the elementary string of string theory, it actually doesn't have any longitudinal vibration. So if you normally have a guitar string, there are two kinds of waves it can carry, transverse waves and longitudinal. Now the elementary string doesn't have a longitudinal wave for a very basic reason. What's a longitudinal wave? If you take something made of atoms, in a longitudinal wave, the atoms can be made closer and further like this, right? And that's a longitudinal wave. Why doesn't the string have one? Because the string is already fundamental. It's not made up of anything else. If it was made up of atoms, then you could do this to the atoms, right? But a fundamental object can only be deformed in its shape. It can't be having a longitudinal mode. And none of the strings of brains have a longitudinal vibration mode. Okay, why is that important? Because then all my oscillations have to be transverse. And now you can already see something interesting qualitatively from this picture. If this is the non-compact direction, right? This is the compact direction we're talking about. In the non-compact direction, this is, let's say, r equal to 0, and if I go here and here, I'm going to bigger r. But now you see the magic. There is no way to put momentum on the string without bending it either one way or the other. It has to go somewhere. So the whole thing cannot actually sit at r equal to 0. It has to go to other values of r. It has to spread out a little bit. And the more momentum I want to put on it, like the more energy I want to carry on the wave, the more the guy has to spread out. And now you start seeing the magic. If I start putting more and more charges to make a bigger and bigger black hole, okay, this kind of guy is going to spread out more and more. And you can see, if we'll now go do the numbers, and we can actually write down the actual wave functions. All we have to do is to find a wave function of a string carrying vibrations. But now with all the gravity and everything, we can't afford to say we're working at weak coupling. With all the gravity and everything included, if we can write the wave function of a string like this and just see what it gives us, does it give us a horizon? Does it give us a singularity? What does it give us? If it still gives us a horizon or a singularity, we haven't solved anything. We'll still be in puzzle. We'll still have our puzzle. But in fact, we'll find if you actually write, these are all the states you have. When you actually write the metric that they create, you will not find a horizon and you will not find a singularity. Let's see how the calculation is done. So again, this is what I just said. If you could actually have a longitudinal wave on the string, then you don't have to go left or right here. And therefore, from the point of view of somebody who can't see the compact dimension, it looked like a point-like blob, and the metric would sort of again go down to a point, and you'll get a normal point-like singularity in the center. That's the standard picture. But actually, we have seen the only way to put the momentum on the string is to make it go left and right. This is the covering space. The actual space is compactified after every distance L, right? So the actual piece, this piece in the real space lives here. This piece lives here. This piece lives here. So the string is continuous, so you can see what happens in the actual space. Here I just open it up to show it. In the actual space, if this is the covering space profile, the whole thing goes like a slinky. It sort of goes around like this. Okay, so can you see that? It just sort of winds around like this. But you can see it's spreading out all over the place because if I do this to the string, this piece is over here, this piece is over here. It's spread out over some bit. And so in fact, instead of getting this, I actually get something which is created by a source. And the source is not like a point. It's not all at r equal to 0. It's a distributed source which is like this kind of a strip. Okay, so I drew the strip here. And let's see if we can actually find this solution. So I'm missing some slides here. Can I just see why my slide wasn't showing up? Is this visible up here? If I do play, okay, it came out. Okay, so here's how you actually do the calculation. If you have a string which is straight, the metric of a string which is standing straight is actually known. Just like if you have point mass, you get the short shell metric. If you have a string, you get a similar metric. It's just like Newton's laws, right? If you have point mass, you know the potential. If I give you a string mass, you also know the potential. Okay, so you can compute the metric of this guy. It's very interesting that the metric of a string carrying a wave is also exactly known. There's something called the Vachaspati transform in a string carrying a wave. This was done way back in the days of cosmic strings. That's also known. What we have actually are many strands of the string, right? So we need many strands, and we need the metric produced by this combination of strands. It turns out that is also known. If you actually have many points in Newton potential, if you know the potential created by one point, you can just superpose them to get the potential from all the points. It turns out the same kind of magic works here, and you can actually make the metric of a bunch of strands. Well, that's good. That's all that we have, and because there are so many of them, you can sort of smear them to make a continuous band, and then you can actually find the metric for each of those states of the string. Okay, so everything has been done in pictures. We didn't really need anything, but for once actually, let's look at a formula. You don't actually need to read this, but this is the complete solution. So all the things, all the states that you want for the black hole carrying two charges are here. If I give you a string profile, I can describe that by a displacement f, which is a function of let's call this coordinate x. It's a function of x minus t. X minus t because the wave is moving up there at the speed of light. Okay, so at t equal to 0, this is the profile. So if I give you the profile, I gave you this profile. That profile you put in here, and you can see that there's a source here, x minus f. So there's a source at the location of the profile, but the source is distributed, so you have to integrate over all the entire profile. Anyway, you take these functions and you plug them in the metric in these places, and well, whatever that mess is, you don't need to see it. You know the entire metric. Okay, good. So we have found all the states of the black hole. There's nothing else there. There's no other way you can get any state out of string theory with those charges. And so let's look at the lessons we got. Again, back to pictures. So the whole thing looked like a slinky, and different microstates actually have different shapes. So different microstates have different shapes near here. They are not all the same. You got complete set of hair. Hair meant that different states of the black hole are supposed to have different structures, right? There they are. There's no black holes have no hair kind of business going on here. And then if you try to see what's the area where this mess is happening in general, up to here everything was the same as if it was a point, there's some area where the string was going around, right? So if you just try to measure what the area of this boundary region where the string was fooling around, if you take that area and divide by 4g, you get of the order of the entropy. Okay, so now we see that the size of the whole string, so firstly if you look at that metric, there's no singularity anywhere. You also find no horizon. If there's no horizon, what happened to the whole Beckstein thing? Well, if you take the size of the ball, that area upon g, order of magnitude wise, is actually equal to the entropy. So there are many constants here like the string coupling, and the string tension and so on. They all cancel out and they leave you a beautiful fact that doesn't matter how many charges you take, the area upon g is always this. So if you increase the charges, the string just sort of winds around more, spreads out more, and you try to make a bigger black hole by having more charge in there, which means more mass in there. The whole thing, the string just becomes bigger. It's always of order the horizon size. It never actually shrinks to a point, making a big horizon around it. So the whole traditional picture of the black hole has just vanished. And of course, if that's true, all the information paradox is gone as well. If this was going to be true for all the black holes you could make in string theory, there's no information puzzle. Everything basically looks like a planet. Okay? And these are all the states because they've counted the entropy. We know this is the only way to make states out of making a bound state of winding and momentum. And so for this two charge thing, everything is solved. The question now is, if you make like three charges, you take strings and momentum modes and some branes, right? So then people keep asking, will it work in that case also? And that's sort of an ongoing game because that's obviously complicated. So here I just told you that, normally you had a vacuum horizon and now you don't have a vacuum horizon. So it's just like a planet with some surface. And so then there is no information puzzle. So that information puzzle is removed, okay? So in fact, you can now do this with lots and lots of kinds of branes, and people have been doing it with 3 charges, 4 charges, and so on. And in every case that people have tried so far, you never find a horizon. Okay, so that's the fuzzball story. But there's a lot of physics now that we have to extract from this. So let me see, what time should I stop? I think I started at 5:40. Should I start at, say, 4:40? Should I end at 5:30? I'll stop at 5:30? Okay. Okay, so let's start to extract some physics from this because we've just seen something little striking that these things like spread out so much, and let's go back and do some qualitative physics from this to extract some lessons. I mean, looking at the technical stuff of making more fuzzballs won't help us with our goals here. So let's see what happens. Let's go back to what we talked about, the Bookdal theorem. We said if you take the reason people always thought there was no hair, you only get black holes. If you try to make a sphere of perfect fluid whose radius is less than 2¼ m, so outside the horizon, then what Bookdal found was at the surface the pressure is 0, but if you integrate the pressure gradient, the pressure has to keep rising as you go in, right? The gradient of the pressure will rise. If this thing was 2¼ m or smaller, as you integrate the pressure in with this equation, at some point P becomes infinity, and then the whole thing has to collapse. Okay, so you're not supposed to be able to make these things stand like this. So how are we getting these guys, and why are they not collapsing? What is the structure of these fuzzballs? Let's just play with their properties. Okay. So here's an example. It's the kind of example that I talked about in words in the public talk, but now we'll do it in technical things. So here's a very simple example. If you know the Schwarzschild metric, you can take time to I times time. You can write tau is equal to IT, and this part is what is called the Euclidean Schwarzschild metric. So R0 is 2m here. So if this sign was a minus, you know this would be the Schwarzschild metric. Just ignore this for the moment. If I put t to I tau, then this will actually turn to a plus, and this is called the Euclidean Schwarzschild metric. If you look at this metric, it has a very interesting property. It again seems to have a problem when R becomes equal to R0, but actually doesn't. If you look at this metric, it actually looks like this. There's this circle. Now tau is a compact circle. I take the circle, not only did I do t equal to I tau, I also made it periodic. And now what happens is, it's a circle like this far away, and this is the same picture as I was explaining in my public talk, so let's go back to that. You imagine this room, you cut a big ball from the middle and you throw it away. That's not part of your space-time. That's this hole in here. But everywhere there is an extra circle, a fifth dimension hanging out everywhere. Okay, so if I just had, otherwise if I just cut a hole out, you might think if I go there, where will I go after that? I'll fall in. But no, I have this extra circle. As I come close to this boundary of the region I cut out, I smoothly pinch it off and close it like a smooth cigar. That's this picture here. Okay, so from every direction you come, you close off like a cigar. So there's no problem. You come here, you just go out here. Okay, that was the qualitative picture, but this is the actual metric which does it. It's a solution of the vacuum Einstein equations. Plug into the Einstein equations in 5 dimensions now. This is 4 dimension, this is the 5th time. It actually solves the Einstein equations. Okay, so this is a well-known solution, nothing surprising about this, but we're going to see this in a funny way. What's the funny way? We'll do dimensional reduction. It's a solution in 4 + 1 dimensions, but you know if you have a compact circle, the size of the circle can change at different points, but the size of the circle can be thought of as a scalar field. Where the circle is big, you can say the scalar field is big. Where the circle is small, you can say the scalar field is small. So you can think of this problem as something in 3 + 1 dimensions, which only includes t, r, theta, phi, and the size of the tau circle, this direction, I'll think of it as a scalar field. So you take the metric of the tau direction and you write as in terms of a scalar field, and now you can see a bigger circle means a bigger scalar field, smaller circle means a smaller scalar field. So that's what's called dimensional reduction. Okay, so a person who's really working in 3 + 1 dimensions will then, I just wrote the metric out, I don't really need to see it, but if you do all that, if you have a scalar field, the full 5-dimensional action I started with will look like a 4-dimensional Einstein action and the normal action for a scalar field. Okay, this is called dimensional reduction, and why are we doing this? Because, of course, in our case, we have extra dimensions, right? All the strings are all wrapped in the extra dimension. So we are looking at extra dimension physics using this toy model. Okay, so because I have a given solution here, how the compact dimension is changing in size, the phi is not the same everywhere. So phi does have a gradient. If it has a gradient, it also has a stress tensor. So good, I have a metric in 3 + 1 dimensions, and from the point of view of 3 + 1 dimensions, there's a scalar field, the size of that circle, and it's changing, so it has an energy, and good, there's some energy, there's some metric, and they satisfy Einstein's equations all together using the standard action. Well, if you compute the actual stress tensor, it's sort of diagonal with these functions, and these functions all blow up as you come here. Okay, so as a person tries to decompose this 5-dimensional solution into a 3 + 1 and an extra compact circle and thinks of that guy as a scalar field, he will say, hey, look what's going on. The pressure is diverging as I come to this place. You see the pressure is diverging? There, so diverging as R goes to R0. And then if he was Bookdal, he would say, I don't want this solution. If the pressure diverges, it's a bad solution. But it's not a bad solution, it's a completely smooth solution in 5 dimensions. There's nothing going wrong anywhere. What goes wrong is that the split into 3 + 1 and the extra circle, the split doesn't work anymore. In some sense, all the fuzzball magic works this way. You have solutions which are completely smooth in 10 dimensions, but when you try to see it as 3 + 1 dimensional physics and some effective matter, that matter looks crazy. The matter looks like as if something is singular, the pressures are blowing up, some tensions are becoming negative, it just looks bizarre. But that's why people never thought of those guys and they never actually found these solutions. But if you directly look for solutions in 10 dimensions, well, there they all are. And so that's the magic. The extra dimensions work in very non-perturbative way because they have sort of shrunk here and closed here and they do all these things. And if you try to see how many solutions of this kind there are, well, that in the simple case of two charges gives you all the solutions. Okay, and they account for the Beckstein entropy. So it's the fact that the extra dimensions don't trivially factor out. It's not like a circle is like a circle everywhere. Somewhere it disappears and somewhere it comes up and so on. That's the solution that people had missed. And if you look at them, you actually get all the guys which actually describe the interior of a black hole. So that's the whole Fuzzball story, and many people have worked on this. I tried to list some of them over here, and in every case which has been done so far, you never get this region now which has a negative energy particles possible, where you create Hawking pairs like this, even with small corrections. We had seen if you create Hawking pairs like this with small corrections, even if you allow small corrections, you cannot get out of the information puzzle, but now you don't have that. You have something which is like filling up the entire region, and now it radiates like a planet, and the conjecture would then be that even though we've done this for simple cases and some of the more complicated cases, the conjecture would then be that it doesn't matter what you try in string theory, you take this brain, that brain, you do whatever you like, you'll never be able to squeeze them inside a horizon, you just can't make a horizon. So that's interesting. Normally you would have worried about getting a singularity in the theory of quantum gravity, but what Hawking showed us is the trouble really comes from the horizon. And now what you're finding in string theory is that you just can't stuff things into a horizon, because you try to take a bigger mass, and the horizon area is that much bigger, you try to squeeze them, and the guys just swell up, and they just don't squeeze in there. And if you can never actually make a horizon, then there's no puzzle. Okay? And so in all the cases that people have tried, not once have, in all these like 18 years or so of doing this, we've never been able to make a bound state which actually shrinks inside its own horizon. Okay, so that's the fuzzball game. But now we have some more deeper abstract physics questions to ask. Again, we talked about this briefly in the public lecture, but now let's do it a little more technically. Why did our semi-classical intuition break down so badly? If you took a shell and you let it collapse under its own gravity by putting it in a classical simulation of Einstein's equation, it would seem to smoothly collapse, and the light cones would turn inwards, you make a black hole, and it has to keep going in. But here we are saying, no, that guy becomes a fuzzball. So somewhere we have to say, why did the classical intuition break down? If we can absorb that lesson, then we really know when to start using this new magical physics, and when we were good with our normal classical physics. That's something we really need to understand. Okay, so what happens is if you take this collapsing shell, you find there's a path of tunneling, quantum tunneling, to these fuzzball states. You can already see that in pictures, right? We had a compact circle which was like this. To start with, it's everywhere like a drinking straw. But if you do this and you pinch it off like this, start looking like that other metric I had shown you. Right? This is a tunneling process. You can actually take an extra direction like this, you can pinch it somewhere and change the topology. When you change topology like that, it has to go through a quantum tunneling process, and there are processes like this known. There's something called a bubble of nothing formation, where you start with this and then you tunnel into this shape. So you can actually estimate tunneling amplitudes. In simple cases, you can even compute them exactly. So actually there's a tunneling path from here to here. But in fact, the probability of tunneling is extremely small, because you have a macroscopic object and that's trying to tunnel into another macroscopic object. So even though there's a path to tunnel, like a path like this, the probability of tunneling is very small. But how do you compute the probability of tunneling? The probability of tunneling is always computed as an amplitude for tunneling mod square in any quantum mechanical problem. And the amplitude is then given by e to the minus the action for tunneling. So if you compute the classical action along a tunneling path, e to the minus s is the amplitude, and you square that, you get the probability of tunneling. Okay, so is there some way to estimate the action for tunneling? Well, the Einstein action looks like this, right? It's 1 over 16 pi g, but I'm not doing numbers right now. So 1 over g, curvature scalar, and d4x. Okay. Let's see if there's anything interesting we can pull out of this. So all the length scales here we'll put to be order gm, because all the physics is happening on the horizon scale. So let me do that. So the curvature scalar has units of 1 over length squared. People are familiar with that? 1 over length squared for curvature scalar. So you can see what I have done here. This g is over here. The curvature scalar is 1 over this length scale squared. And the d4x, all space and time intervals I've put to be again order gm. So I get gm to the 4. So can you please check, you get 1 power of g and 2 powers of m. And 1 power of g, if you put c and h bar to 1, is like 1 over m Planck square. So it's really m over m Planck square. It should have been a dimensionless object, so it's nicely dimensionless. It's the mass over the Planck mass squared. And you can see the probability of tunneling is so small, right? E to the power minus mass of black hole upon Planck mass squared. Okay. This is a huge number, so this is very small. So that's the probability for tunneling. It's like we haven't done factors of order 1. So up to factor of order 1, this is what it looks like. So it's very small as expected, but as we again noted in the public talk also, there are many, many different fuzzball solutions we can go to, because there are so many different states, and in any quantum process, there are many different states. You've got to sum the probability of going to any one of them. Okay, so I have to multiply by the number of possible final states, and that's where the magic comes in. The number of possible fuzzballs given by the Beckstein entropy, and that was an abnormally large number. We had this puzzle that the entropy of black hole is so big that normal matter has much less entropy for the same mass. So there's such a big entropy for these guys. Well, how big is it? It was area over 4g. If you actually work out what the area is like gm whole squared. And there's one g at the bottom, so you get 1 power of g and 2 powers of m. In fact, if you work it out, putting it back in terms of Planck length, it's like this. And now you compare this with this, and you see, hey, with black holes something funny happens. This wouldn't happen for a normal object. That's why a big star wouldn't turn into another big star or something, because the probability is very low. But the entropy is not particularly big. But for black holes, we've always known the entropy is this phenomenally big number, which we never knew what to do with. But now we can see that there can be a cancellation. The small probability of tunneling can be overwhelmed by the large number of final states. In fact, what we should be doing is multiplying the probability of tunneling by the number of the final states, and so it goes like this. And you can see we can actually get a probability of order 1. These two can cancel. So this is why black holes are actually not really classical objects. It may look classical because they are big, but in fact the bigger you take the black hole, the more the number of states it has, and the number of states grows so rapidly that in fact if the entire probability of going through these tunneling events is actually not suppressed at all. So in fact you can even prove through some indirect arguments, so it's not a complete rigorous proof, but doing some old work of Cross and Wilczek, we actually proved that the coefficients here are exactly equal. This is 4 pi. You can do the calculation of tunneling to show this is 4 pi, and then in fact the probability is cancelled and you actually get something of order 1. For special families of fuzzball states, people have actually gone and done this kind of tunneling between families of fuzzballs, and they see this enhancement of entropy. And this entropy multiplication you can actually see in families of states and so on. So okay, so this is an important lesson for us to absorb. Let me just give the lesson in a different way. Normally you have in a path integral, when you write a path integral way of doing quantum mechanics, you compute, let's say, z, a path integral. It's integral over all the possibilities. In a theory of gravity, you integrate over metrics. Then you have action, which is made of metric and maybe any matter fields, whatever you have, right? So normally when we start doing the classical approximation, we say, look, the action is very big, because if you put back the h bars, there's a 1 over h bar there. So we say this is the guy we really care about. This is the measure factor. That's order 1. So we ignore this. We minimize the action. We say that's the classical physics. If you minimize the same as the classical action, you get Lagrange's equations. Why is that not working for black holes? It's not working because if you look at the measure of the path integral, the measure counts what? It counts the number of states that are relevant to the process. Okay, so if the entropy is S Bekenstein, the number of states relevant to the process is basically exponential of the Bekenstein entropy. Okay, so normally the measure is order 1, and this is order 1 over h bar. But if you go back and see why the entropy of the black hole was so big, it's because there was an h bar in the denominator. It was a very quantum gravity effect. If you go back and see when I wrote down the expression for the entropy with the h bars, actually there was an h bar in the denominator, and then you find that this action, which we had estimated by doing all the g's and m's, is actually exactly comparable to this action. So if the measure term is not actually suppressed compared to this, you cannot actually extremize this and ignore this. And so all the troubles we were having this far with black holes is because we kept working with the classical action, ignoring this guy, extremizing this, and getting the classical equation of motion. The guy just goes into a singularity, and then everything is blown. But the point is, you actually can't decouple this first, because we've always known that this is a big number. So in fact, we should have worried about this long ago. This doesn't require you to have the fuzzballs. But the problem is that, yes, if you have all those states, but you can't see them, you don't know what you are counting, even though you know that S Bekenstein is a big number, you don't know what to do with it. But now you can see that those states are just ordinary states in a theory. They're just like states of some string doing this. These are these states. And if you have a large phase space of these guys, then the collapsing shell, as it's coming in, it doesn't want to keep going in. Its wave function can transition to this one, can transition to this one. If you have many different places to which you can transition, well then, you have to explore that entire space. And instead of the wave function going in like a shell which goes in, the wave function instead spreads over this large space of new states which are now available. Whenever there's some new light particles coming in, the dynamics gets altered, and that's basically all that has happened. So in that sense, the black hole, treating it like a classical object was never the correct thing to do. And now we see that with string theory, by doing simple examples and looking at the structure of the black hole, we see that that was explicitly wrong.
What about the usual Penrose diagram? Are you saying that there was a...
It's wrong. The inside doesn't work. Okay, so let me pause here because it's close to 5:30. Let me take a couple of questions. Maybe we can take a short break and then come back for the rest of it. Are there some questions I can take now? Yes.
Sorry, is the idea of Fuzzball observer dependent?
No, nothing to do with observer. So in fact, in black holes, people have, in the early days, often talked about, what does a black hole look like to this guy or that guy. That never made much sense to me because finally there has to be a quantum wave functional, right? I mean, there is a thing there, and it's a covariant thing. And everything here is completely covariant. When we wrote down the metrics, let me see if I can go all the way back to the metrics. This is just a normal metric which you can write in any coordinates. And in some sense, that's the only way it makes sense to me. There's an object, and of course, it can depend on how you measure the guy. That's the question of interacting with somebody and so on. Okay, I think I lost that. But I showed you the metric of these fuzzballs. It's a metric like any other metric, like the way you like a metric for a star. That's what it is.
So the time it takes for an object to cross the event horizon is not different depending on which
Okay, so let me see if I understand that correctly, because firstly there is no event horizon now, right? So these were the metrics.
So
Yeah.
the region, for example, R equals to R0.
Yeah, so let's take, so these are the metrics and they're completely covariant, right? You can just they're a metric like any other metric, and then this is what the actual objects look like, right? So the time to fall from infinity up to here is pretty much the same, right? When you come to the horizon, there's nothing very different outside. Outside looks almost like the Schwarzschild metric you would have gotten. In here, once it comes in, all kinds of interesting things can happen. But that's like falling inside a star and then wondering what happens. For that, you have to know something about the star, right? Then you have to worry about the structure of the fuzzball. And leading on to what you can say is it basically absorbs everything. And that's because it has a very high density of states. When the level density is very high, it basically absorbs everything for entropic reasons to a very high degree of freedom. So it's 99.99% absorptive. And so to that extent, for something falling in it to first order, it looks like a black hole. But there's no information puzzle, because that was a puzzle of things coming out from the vacuum because of pair creation. Well, nothing like that can happen because there's no place here where you can actually have a particle having net negative energy. So that never happened.
So if R doesn't go to infinity,
So it never goes to infinity. The GTT, if that's what you're asking, the time component of the metric, it goes close to 0, but never actually becomes 0. And if you actually want to see how much it is, you can actually just look in there. So if you look at this, the actual metrics, the GTT, what happened to this guy? Sorry. Okay, I don't know what it did. But if you look at the GTT, it has a harmonic function in it. It sort of goes small, and it never actually becomes 0. Okay, more questions? Yes.
So when we start to consider the transition from the usual case where the tunneling was negligible, and then to the case where the high number of states
Yes.
becomes considerable, and then it can turn into a fuzzball.
Yes. So what about that? That's what.
What is the stage that
You're asking why did that happen?
mass that triggers the
Right. So so you can see it in any of these ways, right? Either you can look at if you look at some general system, suppose I give you some system and I ask you, will the large number of states create a trouble for me to use a semi-classical approximation? You first can estimate the classical action for the process of tunneling or whatever transitions you're looking for, some transition probability you look at. And then you look at the phase space of states you can go to, which you get from here. And if the two are comparable, you can say, hey, I can't just say that the probability of transitions is small. So you can either directly look at the numbers here, or you can actually say, I take the number of states which you can go to, that was the number of fuzzballs. And then that was some e to the power s Bekenstein. And then take the probability of transition, which was p, which was e to the minus some m over m Planck square. And this was also of the order of e to the m over m Planck square. And if these two coefficients are comparable, then you can say that the transitions are order 1. And if this number is small, like happens if you're looking at a star, the entropy is much lower, and the probability is still big, is still suppressed highly, then this is completely irrelevant.
What I'm confused about here is that, for example, for the number of fuzzballs, it looks like we just have the mass. But for an object with the same mass at different radius, it could might not be collapsing to a fuzzball if it's not that compact yet. So
Okay, so you're asking about how does a fuzzball actually form? Yeah, so we'll be talking about it. Actually, in the next part when I come back, I'm going to now go into a more conjectural part with, with what we know about fuzzballs, we'll try to now make pictures. What happens to something falling in? Where should it try to turn into fuzzballs, and so on? And why does it turn into fuzzball? That's the part I want to talk about next, after the break. Yeah. Yeah, that's very relevant questions. That's what I'll talk about.